Okay, thank you everyone. So my name is Chen and I come from Purdue University. Today I'm going to present the work for done by the Ian James group and which is from the Shanghai Jiao University and Stevens Institute of Technology. So the work is the Army x86 games accelerating binary translation using software owning validated flag speculation. To begin with, the ARM dominates the mobile market, powering nearly every smartphone thanks to its efficient integrated design. On desktops, x86 still holds most of the market, but that's changing fast. The Apple M Series Max and the new Windows on ARM laptops are pushing ARM into the PC space. The problem is that the software isn't keeping up, as shown in this figure. As ARM hardware gains ground each year, the share of legacy application, especially the games with native ARM support, barely moves, stuck in the low single digits. So while ARM hardware footprint grows, software compatibility lags behind, creating a widening gap that risks the user experience unless translation or recompilation solutions fill the void. As ARM PCs become more common, they hit a harder barrier. x86 programs can't run natively on ARM. This forces a choice: either rewrite software for ARM, which gives top performance but is costly and time-consuming, or rely on the binary translation tools like Rosetta or Box64. Translation lets unmodified x86 apps run, which is essential for older or closed-source programs, but it comes with a speed penalty, especially when emulating tricky features like x86 eFlex. Right now, developers must choose between full performance or broad capability. Our work asks if it's finally possible to have both. Profiling on optimized QEMU reveals that eFlex emulation dominates translation overhead. 25% of instructions in this column and 80% of the SGen from this column and 79 in a physics kernel are just for lag bookkeeping. Since each x86 flag update explodes into several ARM instructions, some kernels see a 174 times jump in instruction count. To show the impact, we tested two micro benchmarks, one that updates flag every step, and one that avoids eFlex. On the native x86, the flag-heavy version runs 40% faster. But under QEMU on ARM, the flag-free code is 36% faster, finishing in 295 seconds versus 460 seconds, highlighting how eFlex emulation is the main performance bottleneck in translation. Our profiling shows that the flag emulation can eat up in nearly 80% of the dynamic instruction on ARM, which is the overhead. So why is the overhead so high? It comes down to three key mismatches between x86 and ARM. First, the x86 instructions set multiple flags automatically, even if the one is ever used. Translators that reproduce all of them waste the cycles on unused bookkeeping. Second, x86 updates flags for free with each instruction, but ARM requires explicitly instruction to set or test each flag. This causes the code size to balloon, especially in tight loops. Third, some x86 flags like parity and auxiliary carry don't exist in ARM, so they require slower helper function. These three factors, unnecessary updates, code expansion, and missing flag equivalents, make the flag handling the main source of slowdown. Solving these issues is critical if we want both compatibility and near-native speed on ARM. These three flag pain points set the benchmark for implementing the translator. QEMU's tiny code generator covers every x86 instruction, ensuring full compatibility, but it emulates all flag in software, creating massive E-flags overhead and slowdowns that prevent real-time performance. Box 64 cuts some of that by running in user mode and use native ARM library for graphics and audio, so it runs many Linux games decently, but its generic flag emulation still leaves it 20 to 30% lower than the native. The third, Apple Rosetta 2 goes further under the ahead-of-time translation and special hardware tricks in M-series chips to shortcut many flag operation, achieving up to 80% of native speed on Mac OS. But the speed relies on the Apple's proprietary hardware, so it doesn't help the Windows or Linux ARM users. So let's move to the design. Existing engines forced us to trade the speed for breadth or accept the vendor locking. Our goal is to end that compromise. First, ecosystem compatibility. Any Windows or Linux x86 program games, CAD, legacy toolchains should launch on ARM unchanged. Second, portability. The solution must be pure software, free of Apple-only micro-operation or bespoke firmware, so it runs on any of the shared ARM64 laptop or desktop. In short, we aim to carry the entire legacy x86 stack on the modern ARM hardware while delivering near-native performance. No source changes, no special silicon, just install and play. We turn these goals into a concrete architecture. At the base, a librarian loads x86 libraries, while an interpreter and dynamic recompiler decide when to interpret code or generate the optimized ARM64. A wrapper rewrites every binary and system call to follow the native ARM conventions. Above that sits a thin x86 machine model, handling virtual memory registers and dedicated E-flag objects, so higher layers can manage the program state cleaning. At the top, an analysis tier runs the whole program data flow and applies smart, hardware-aware flag mapping. The key is how these layers work together. The lower layers ensure compatibility, the middle layer delivers performance, and the top layer squeezes out maximum efficiency. Focusing on the green core, the dynamic recompiler is where we get most of our speeds up. When the interpreter finds a hot block, it lifts x86 instruction to an SSA-style IR, simplifies the code, and adds flag usage info from the librarian before generating compact ARM64 code. Importantly, our profiler data guides this process. Any code that just updates unused flag is skipped entirely. And instructions that only need a certain flag are rewritten to set just these bits. This is how we cut out wasted work and boost the performance. The dashed blue box isolates the single biggest pinpoint we diagnosed, the x86 E-flags. Instead of natively materializing 6 bits after every arithmetic micro-operation, we treat the E-flags as a lazy, taint, tracked field. Each flag starts with an unknown state. The data flow engine annotates it as plain when a direct ARM and ZCV mapping exists, dirty when a minimal helper suffices, or dead when no downstream consumer reads it. Only clean flags generate native condition code. Dirty code defer to a compact lookup helper. Dead ones vanish entirely. At the top page tier, we turn local speeds up into whole program gains. A rolling control flow graph and data flow analysis track flag dependencies across blocks, catching cases that single block analysis would miss. One thing stabilized, a compatibility checker rewrites any remaining tricky flags into efficient ARM conditionals, or combines multiple flag checks into a single micro operation when it makes sense. Since it's all pure software, this pipeline works on any standard ARM64 laptop, but the resulting binary runs almost like they have custom hardware support. In the end, our full stack lets unmodified x86 software run on stock ARM hardware at speed surprisingly close to the native. So here is our flag strategy works in practice. On the left, you see an x86 loop where each arithmetic or compare sets 6 data bits, but later branches only need some of them. Our data flow analysis runs backward through the code, marking each mark as live, needed, or dead, unused. Red boxes show where the flags like parity and auxiliary carry are proven dead or crossed out. This info fits into the compiler, so dead flags are never emitted in ARM64 code, cutting out lots of instructions. Sorry about that. For the flags that still needed, we use lazy emulation. The mean for the size 0 carry overflow maps directly to ARM's NZCV bits and set for free by the hardware. Rare flags like parity and auxiliary carry are only computed if the program actually checks them, saving even more cycles. To validate that our flag-aware translator delivers benefits beyond micro-benchmarks, we integrated into Box64 and deployed the whole stack on a NVIDIA Jetson Severe AGX develop kit. 8 ARM v8.2 cores and discrete GTX 1060 and 30 GB of RAM running Ubuntu 20.4 LTS. We stress that the GPU with Geekbench 6 and the GPU with the Unigen Heaven 4.0 and Valley 1.0 3D benchmarks. The end-to-end game pipeline with 6 diverse Steam titles, the mixed synthetic graphics, heavy and real gameplay let us isolate the raw compute gains, rendering smoothness and practical FPS improvement inside the very compatibility layer we aim to accelerate. On pure compute, our flag pruning translates directly into higher scores. The single core resulting climb 5% and multi-core 10%. Overhead figure tell the story, owning 0.12% extra CPU and less than 1% memory, because most conditional logic now writes on ARM's built-in NZCV bits instead of software helpers. Workloads heavy in branches, the PDF render object detection show the sharpest upstick, confirming that cheaper flag handling, not new algorithm, fuels the win. Even in GPS-bound things, linear CPU translation plays dividends. In Heaven, the average frame rate rises from 57.6 FPS to 63.4 FPS, and Valley edges up to 4%. Stuttering drops because the branch-intensive draw call marshalling and physics loops no longer waste cycles synthesizing dead flags. The CPU feeds the GPU more steadily. Crucially, the CPU cost of our runtime stays at just 0.08%, while memory overhead remains modest. So graphics bandwidth is just left to textures, not translation. Finally, real games confirm pliability gains. Average FPS climb 6 to 12% across Cook, Serve, Delicious, Street of Rage 4, Disco Elysium, Batman Arkham Knight, Dishonored 2, and Hollow Knight. Minimum FPS bumps are especially telling, smoothing out compact spikes and camera pans. because the optimized translator shares up to 79% of flag traffic, and CPU can service game logic and driver thread faster, cutting latency even when the GPU is saturated. In short, our software-only approach pushes user-perceived performance closer to native without touching a line of game code or requiring Apple-style silicon assistance. To sum up, there are three main takeaways. First, our pure software approach recovers most of the performance usually lost to x86 flag emulation by cutting the dead flags, mapping live one to the ARM's native bytes, and differing rare cases we slash up to 79% of flag overhead. This leads to real wins, up to 18 better Geekbench scores and 10% higher FPS in Unigine Heaven, and a 7 to 12 uplift in Steam games, all on a standard JSON severe board with no special hardware. Second, our design is fully portable. Unlike Rosetta 2, every optimization is in the translator, so the same code runs on Snapdragon laptops, Ampere servers, and even on a Raspberry Pi without any changes. This portability is key to bringing the huge x86 software ecosystem to the growing world of our ARM PCs, no rewrites, no compromises. Finally, this approach isn't limited to games. Any branch-heavy workload like control system, VR, or some AI inference can benefit from our flag-aware pipelines. Down the line, we can add more profiling or machine learning to optimize further, but the core result is clear. With careful analysis, pure software can deliver near-native x86 performance on any ARM chip, unlocking the decades of legacy software. So that's all for today's presentation. Thank you.
Okay, thanks Chen Peng for helping sharing this great talk with us. But for this special case, since the presenter, the author is not here, so we will skip the Q&A session for this presentation. And the authors asked me to convey a message that if you have any question about this work, please feel free to send email direct to them for further discussion. So now